Today we're going to take a look at some of the higher order functions, cubics, quartics, things like that, and how we can use technology to help us analyze them, saving us the time and trouble of doing an algebraic method or a graphical method. Let's use some technology. So we're going back to the same place we went yesterday, so that the Desmos site, whether it's on your app or whether it's on your computer, and you're going to want to open that website up. And we'll go back and forth again, sort of like we did yesterday, from one to the other, and make life a little bit easy for us. So what do we got today? A patient's reaction time in minutes to a small dose of a certain drug is given by a nice cubic equation where T, oh, that's a typo, sorry guys. That should be the letter D there, okay? Just a little typo. D. D is the amount of the drug in milliliters that is absorbed in the patient's bloodstream. So what type of function is D? Well, it's got a power of 3, so we know that's cubic. We don't want to forget about those things we can just look at and figure things out, right? Which finite differences are constant? We'll be working on tables. That would be your third differences, right? Cubic is third because it's the power of 3. End behavior. What letter B? End behavior. As we move to the right, our leading coefficient is negative. That tells me we're going down. As we move to the left, our leading coefficient tells negative on one side. It's cubic, degree of 3, so it should do the opposite on the other side. Okay. Part D, what's the optimal reaction time? Well, now that's not something we can look at and figure out. Here's where my technology is going to come in helpful. So let's put this equation in. We're going to go back to y equals. Even though it's got r's and d's, we know these should be y's and x's for our technology's sake. So negative 0.6. So make that an x. It's the power of, so we need the a to the b this time, okay? This one right here is your exponent button. And just so you know, power of 3 plus x, and we want to square it. There's my nice parabola, or sorry, cubic. And what do they want? They want to know the optimal reaction time. That'll be the best reaction time. So our best reaction time is the highest that this thing gets. So on ours, it's going to be right there, that dot, right at the top. So 1.111 and 0.412. I'm going to write down those numbers so we remember what they are. 1.111 and 0.412. I believe that's what the numbers were. Just check. Yep. Okay. So what does that mean to me? What is the optimal reaction time? How much drug was absorbed? So our reaction time is R, right, which we said was Y, which would make that your reaction time. Oh, sorry. Yes. That's your reaction time. How much drug was in? That was our X. This would be the drug in milliliters, and this was our reaction time in minutes. Okay, so if I put that into a sentence, what's the optimal reaction time? Okay, 0.412 minutes. Optimal time is 0.412 minutes before this drug reacts with you, and with a dose of 1.11 milliliters. Okay, assuming that a negative reaction time is not possible, right, that wouldn't make sense, right? What are the restrictions on the domain? So restriction on the domain is what part of the graph actually means something to us. Well, I can't have 0 drug in my system, and I can't have negative reaction time, so I can't go below there. So the only part of the graph that really matters to me is from this dot to this dot, right? From here to here. That's my restriction of my domain. If I can figure out what those dots are, I can figure out what my domain should be. So let's take a look. We got that dot we know is 0. This dot over here is 1.667. Okay, so we're going to write down for part E, our domain should be all real numbers from 0 up to 1.667, we just said, right? What the numbers were? Let's check. Yeah. Okay, so there's my domain. What does this mean in a practical sense? Okay. Remember what X represents. X is our dosage, right? Any dosage larger than 1.667 milliliters will have no effect on reaction time. Because that's what's happening there, right? Once I got a reaction time of 0, it's not reacting anymore. I can't have negative reaction time. It doesn't make sense. Okay, so I have to have a dosage between 0 and 1.667 to have some sort of reaction. Okay, you gotta try the next one. Same ideas. We use technology, can problem solve a little bit, can figure some things out. Okay, we got a box no top being made out of cardboard by cutting squares from each length of the corners. So in a practical sense, this is my cardboard. This is, oh, I think that's the big one. This is 30. And this is 20. And I'm going to cut out a piece from here and a piece from here and then fold that up. And I don't know how much I'm cutting out. These are my X's. And I'll end up with a box. Right, a box that kind of looks like this. And make it in a box. Okay, and it's 20 by 30. And it's X tall, right? That's the piece you cut out. So these are X by X. And that's what's happening here. Don't stress too much about that. We're given an equation. Determine the volume if the side length of each square is 6 centimeters. So, what could I do? What could I figure out the volume with? Well, if X is 6, I can use my equation if I wanted to. I could say 6 times 20 minus 2 times 6 times 30 minus 2 times 6. That would totally work. We can do that. Or, we can use some technology. That would work too. And make a new equation this time. My equation would be y equals x bracket 20 minus 2x, other bracket, new bracket, 30 minus 2x bracket. And I can't really see anything, so maybe I'll zoom out a little bit. Oh, there's my nice, oh, it's a cubic. It's a weird looking function, eh? Look at that, all the lines that go straight up and down. Kind of bizarre, right? Kind of hard to recognize this one. So this time, rather than just zooming in and out, I'm going to set my scale. So I'm going to use this thing up here at the top, the wrench. Okay, my x-axis, I'm going to change the numbers. I want to make my x-axis narrow. I'm going to change it from 0 over to, I'm going to turn this one into, let's backspace that. Backspace. Okay, maybe let's make this 20. And I did that because when I looked at the picture, I saw that it wasn't very wide. Okay, so if I get rid of that now, I can look at my function. That looks more reasonable. I might need to zoom out a little bit more so I can, there we go, I can see my function. But you see how I can use the wrench tool to change the settings, the viewpoint, if you will? Okay, back to our question. We were asked to figure out, oh, what happens when x is 6? Well, if I have my picture now, I can say, x equals 6. Tell me what it is. Oh, there it is right there. Where's that gray spot? There, 6 and 864. Now, some of you are probably saying, well, I just punched my calculators way faster. And you're right, it probably would be way faster in this case to punch that in your calculator. But for down the road, when I need to do something else with it, I already have the equation built. So it's sort of your prerogative which one you want to do for that. All right, part B. Part B says, graph the function, determine the length of each square if the volume is 1,000. So this time I know the V part, or the Y part, is 1,000. So let's go see. If I make Y 1,000, there's my V, okay. What are the different X values I could have? And if I look at this, there's actually 3 of them, right? There's this one up here. So 2.929, we're going to write that one down. X equals 2.929. Okay, X could also equal, if I go to the next one, this one here, 5. X is equal 5. If I go to the third one, way over here on the right-hand side, I get 17.071. 17.071. All 3 of those X values create my box of 1,000 centimeters cubed. But there's one problem. Remember our objective in the question was, how much can I cut off from the corners? So we have to go back and think in a practical sense. Is it possible to cut all three of those off and still make this box? So if I look at the first one, if x was that, let's just call it 3. So 2.929, but call it 3. Could I take 3, put 3 in here, and make this still a possible box? Well, I'd have 3 outside. I'd have 20 minus 2 times 3, so 2 times 3 is 6. I'd have 3 times 14 times, if I put 3 in the other one approximately, I get 24. Yeah, that's possible. I could have those dimensions. That's doable. What about if I had 5 for all those x's? X was 5. I'd get 20 minus 10 this time, and 30 minus 10, which would be 5 times 10. I could do that. That's possible. But if I try that third one, x is 17, I get 20 minus 2 times 17. 2 times 17 is 34. Can I cut 34 centimeters off a box that's only 24 centimeters wide? No, that's not possible. Okay, so even though it's a solution on our screen, this is something we call an inadmissible answer because it's not practically possible. What values of x can I have to form 1,000? I could have either one of these two, but I could not have 17.071. It's not possible to cut that much off. Okay, so you have to start thinking about your answers a little bit sometimes. All right, let's try the last one. Example number 3. The members of the Sickle family competitive card players. They keep score using a system of positives and negatives. Maya's score can be modeled by this lovely equation. Well, let's get our graphing calculator. Okay, let's clear these ones out. Get rid of that one, that one. Hey, what are we going to put in here? Y equals x to the power of 3 minus 10x squared plus 24x. I can't really see it, so let's zoom it out a little bit. Okay, maybe I went a little too far there. There we go. We got a nice function there. X cubed. Make sure we put that in right. Okay, it looks good. What do they want to know? After what game was Maya's score 0? Okay, well, we can figure that out. It's 0, well, at the very beginning. I had 0, 0. That's obvious. And again, over here. Oh, that's not 0. How about that one? Yep, that one is. How about that one? Oh, there it is. There's 3 of them. So at games 0, 4, and 6. There's 3 times where she had scores of 0. After what game was her score -5? Well, when I touched those gray dots a second ago, I think I found a -5 one, didn't I? Let's get rid of these two. I can't see there. There's a -5 score. So I would say that would be the 5th game, if you will. So game 5. What were the maximum and minimum scores that she obtained? Well, I think her min score we just found, right? I think that was -5. Just looking at that one. Looks like -5 to me is the lowest one. Her highest one was over here on the left. Call that 16 point, call it 17-ish. Okay, so the min of -5, a max of 17. Maybe they can get decimals. We can write down 16.9. We'll just assume they're whole numbers. Hey, and what is the domain of this function? Domain. How far left and right does this function go? Well, x stands for our number of games. Can't really have negatives. It doesn't make sense to have anything below here. As far as we know, they could keep playing all night, right? We don't really know. Maybe based on a practical sense, her last score of the evening was 6 or 7, and we don't know. So as far as we can tell, because it keep going forever and ever and ever, we would have to say for her domain, it's all real numbers as long as they're bigger than 0. They didn't tell us, oh, they only played 10 games or 12 games. And we don't know. Okay, and there's how we can do some technology for some of the higher order functions. Okay, that's the end of this unit. Okay, you have a review left to try. When you're done that or getting ready to be done that, let me know and we can figure out when you do the test. You will have some technology questions on the test, so you have to know how to use this Desmos application. If there's things you're not so sure about, send me an email. And I'll arrange with the teacher to have some sort of device available to you when you're doing your test. Okay.